Hey there everybody, welcome to a video on section 9.1. Recall that the point of chapter 9 is to build up to some ecological models like predator-prey models at the end of the chapter. Section 9.1 starts us on that path by providing language for slope fields of linear systems of differential equations. So this section is mainly actually a callback to chapter 7. In chapter 7 we saw some slope fields of linear systems of differential equations and we provided some names for the kinds of fields that we saw. Section 9.1 just wants to call back all of that language and reset that context for you because we'll need it to study the ecological models at the end of the chapter. So here's the point of section 9.1. Recall back in chapter 7, we spent like all of our time solving differential equation systems that looked like that. So vector derivative equaled matrix times vector. When that matrix was 2 by 2, which meant we had two equations and two unknowns, we could draw slope fields to get an idea of the long-term behavior of the solutions. Those slope fields were drawn in x1, x2 space, so the two axes were labeled by the solutions, so we could track the long-term behavior of x1 and x2 together over time. Back in chapter 7, we saw that what was driving the qualitative nature of those pictures was the eigenvalue structure of the matrix. So section 9.1 just recalls all of that, and what it does is it walks us through all possible cases of the eigenvalue structure of the matrix and provides language for every kind of slope field. So this is mostly just a vocabulary section. Before doing the slope field material, I need one preliminary term, and it should be sort of like an old friend. This should sound very familiar to you. We're going to return to a definition of equilibrium. And this definition is going to be the same as the definition of equilibrium back in chapter 2, right? Recall chapter 2. Seems so long ago, right? It was in the before times, in the long ago, before the disease. Anyway, equilibrium was a very useful concept because it allowed us to analyze the long-term solutions of a single DE, right? We weren't doing systems back then, but of a single DE over time without having to solve the DE. So the equilibrium concept here will do the same thing for us, and it's defined the same way, it's just as cast in terms of systems. So suppose you have a system of DEs like this. An equilibrium of that system is a solution, first and foremost, so you have to be a solution of the system to be in equilibrium, and furthermore, you must be constant. Again, that's the same definition that we used back in chapter 2 and that we got so much mileage out of back in chapter 2, except now this x is bold, and it wasn't bold back in chapter 2. So just to play around with this definition a bit, here is a system right here. It's a 2 by 2 system, two equations, two unknowns. Here is a potential equilibrium of the system. It's potentially in equilibrium because it's constant, right? There's no e to the t or sine t here, right? Just constant 2 up top, constant -1 down below. So in order for this to be in equilibrium, it would need to be a solution of the system, which means I would have to be able to substitute it in and get something true. And similarly for this one. This also, to be in equilibrium, I'd have to be able to substitute it in and get something true. So what I want you to do is pause the video and see which, if either of these, are equilibria of the system. Okay, so assuming you're back now and unpause the video, hopefully you got these two results. Hopefully you got that this first guy was not in equilibrium, whereas the second guy was. And hopefully what you did was you just substituted in to the DE. So when I take the derivative of a constant, then I get 0. That has been true forever, right? Since Calc 1 for you. So when I differentiate this vector, I get a 0 on the top, a 0 on the bottom. Now I have to check, or to ask myself, what if I substitute that vector on the right-hand side? Do I get 0, 0 there? And in this case, the answer is no. I get this vector. However, if I stick a 1, 2 in there for x and do the multiplication on the right, I do get 0, 0. So this 1, 2 guy is in equilibrium. The 2, -1 guy is not. Okay, so again, that's just the concept of equilibrium that I'm importing from chapter 2. So all linear systems have at least one equilibrium, and this linear system here, this matrix A, is generic. Okay, so I'm saying no matter what this matrix is, this linear system has at least one equilibrium. And like back on this page, right, we saw at least one, this 1, 2 guy right here. So if we were in class, the first question I would ask you is Is there a choice of x that always works? Can you think of an equilibrium for any linear system? A vector such that its derivative equals the matrix times itself. So if you think about it a little bit, you'll discover this solution. The zero vector is always in equilibrium. Why is that? Well, because the derivative of 0 is 0, and a times 0 is 0. So you get 0 equals 0. Are there other equilibria? Well, sometimes, like in this system here, right, there was another equilibrium, at least one other one, this 1, 2 guy. So it sort of depends, right? Note, though, that finding an equilibrium boils down to solving this equation. Why? Because the derivative of a constant is 0. And once again, this should look familiar from Chapter 2. Right? In Chapter 2, this is how we found equilibria. We set the derivative equal to 0 and we solved. Well, notice if a has an inverse, in other words, you can divide by a, then you can divide by a. So a cancels with itself here. 0 divided by a is 0, and you get this. So linear systems involving an invertible matrix have one and only one equilibrium. What this chapter does is it notices, right, that the origin is always in equilibrium, and gives language surrounding pictures that are centered at the origin. So all the pictures I'm going to show you are centered at the origin, and this is why. For any invertible matrix, you only have one equilibrium anyway. It's the 0 vector, which in our pictures corresponds to the origin. The 0 vector is the point 0, 0. Oh yes, one last little terminological point here. The book sort of goes back and forth between calling an equilibrium or calling it a critical point. So either term is fine. Now back in Chapter 2, after we defined an equilibrium, the next concept we talked about was stability. That will be the same case here. So recall back in Chapter 2, if we knew what the equilibria of a DE was, and we knew stability information, then we knew everything we wanted to know if all we cared about was long-term behavior of solutions. So the same thing will be the case here. So this is a nice little echo back to Chapter 2 in every possible sense. We just don't have a single DE anymore. We have systems of DEs. Okay, so now in Chapter 9, an equilibrium is called asymptotically stable if, just like back in Chapter 2, it acts like an attractor or a sink. It draws things to it. So in other words, if I knock you off the point a little bit, so I knock you off the origin a little bit, you're going to flow right back to that equilibrium, which again, for now, we're thinking of as being the origin. Now, the one difference between Chapter 9 and Chapter 2 is that back in Chapter 2, we used the terms asymptotically stable and stable interchangeably. We use those as synonyms. Now, in Chapter 9, that won't be the case. I really do want to say asymptotically stable here. We keep the fancy adverb here, The concept of stability I'll define for you in a second. So being stable, though, now is different from being asymptotically stable. Well, if being stable means that you draw things to yourself, you are an attractor. Being unstable, just like back in Chapter 2, means that you're sort of a repeller or repellent. I'm not sure which is the right noun there. Anyway, so you act like a source. Things flow away from you. So if you're sitting at the equilibrium and I knock you off the equilibrium a little bit, you're not going to flow back to the equilibrium. You'll flow away from it. You'll flow sort of like off the page or something. So anyway, it repels nearby points. An equilibrium is called stable if that point is neither a sink nor a source. Instead, if I knock you off at equilibrium, you don't get sucked back to the equilibrium. You don't get shot off the page. Instead, you fall into a stable orbit around the point, and much like the moon orbits the Earth, okay? So imagine the moon was on top of the Earth right now, and then we shot it into space, right? It falls into that orbit around the Earth. So the trajectories look like elliptical orbits, basically, rather than shooting off to infinity or something or being sucked back into the Earth. So let me show you some pictures from Chapter 7 to illustrate these concepts. This system here we looked at in Chapter 7. Here I've got a slope field not from GeoGebra, but from my Grapher app. I like these pictures better because look at this beautiful color coding, right? Isn't that nice? Anyway, so imagine you're at the origin and I knock you over here. What do? You flow right back, right? So the origin here is stable. And by the way, these little arrows here at the very center being crisscrossed, don't worry about that. The Grapher app insists on drawing arrows all the same length, which is why you get a bit of a muddle here when really what's happening is the arrows are getting shorter and shorter, but still pointing towards the origin. Anyway, if you're at the origin, I knock you off the origin in any direction. What happens? You get sucked right back in, right? Because the origin is an attractor or a sink, if you like. Here's the same system, except I have negatived all the numbers, right? So just compare and contrast, right? I've multiplied everything through by -1. And now you get like the same picture, except the arrows are pointing in the other direction. So now, like I take this exact picture, but this arrowhead I moved there, right? So you just reverse all the arrows. This is now unstable. If you're at the origin and I knock you off, where do you go? You flow off the page, right? The origin is repelling points. Here's another picture from chapter 7. We called this kind of picture a saddle back in those days, okay? And notice this picture also, it seems reasonable to call it unstable. If you're at the origin, I knock you over here, where do you go? You flow this way, right? If you're at the origin, I knock you down here, you flow away. So generally speaking, if I knock you off the origin, you flow off the page, basically, right? The reason I wanted to show you this is there is one exception to that. So the saddle points, recall from chapter 7, there was like an eigenvector line, and in this case it was this one right here following these arrows. And points along the less dominant eigenvector line actually did flow to the origin. So notice these points are kind of curving this way, these points are kind of curving this way, so there's like a dividing line, and the dividing line was the less dominant eigenvector, and along that line you actually would flow to the origin. So all I'm saying is, if I'm at the origin and I knock you like right there, you actually will flow back to the origin. So the origin does suck some points back to itself, but it's very rare, right? Almost always, if I knock you off the origin, you're going to shoot off the page. So it still makes sense to call this unstable, even though this is sort of the classic picture of stability. No matter where I knock you off, right, you're flowing away from the origin. Whereas here, again, there's some sort of like little separatrix line here, along which you can flow back. Okay, so I've shown you two pictures of instability. One picture is of asymptotic stability. So I think I forgot to use the adverb asymptotically here, but this is asymptotically stable. Let me now show you a picture of just raw stability. Consider a picture like this. If you are at the origin and I knock you right here, what do? You don't flow back to the origin, right? You don't get sucked back in, but you also don't get shot off the page. Instead, you sort of do this. You fall into like an elliptical orbit. Okay, so we need language for that. So again, this is not unstable because the origin is not repelling you exactly, right? But it's also clearly not asymptotically stable because the origin is not drawing you back in. So when you get this sort of spiral behavior, but it's not a spiral, right? We saw spiral pictures in chapter 7 where you spiraled out of control like that off the page. Here the spirals are completely controlled and they all collapse into ellipses. The trajectories are all ellipses. This is called stability. Okay, now back in chapter 7 also, we pointed out that what might be driving the nature of these pictures is the eigenvalue structure. So let me go back to this system here. In chapter 7, we saw the eigenvalues of this system were -4 and -1. Those eigenvalues are real, they are distinct, they are both negative. And those three things actually are what produces a picture like this. An asymptotically stable, in this case, node. This guy here, the eigenvalues are 1 and 4. Real, distinct, both positive. Those three factors are why you get an unstable node like this. This picture here, the eigenvalues, again, we saw this in chapter 7, the eigenvalues were -1 and 3. They are real, they are distinct, but they are of opposite signs. One negative, one positive. That's how you get this unstable saddle structure. This picture here, the eigenvalues are 3i and -3i. They are not just complex, they are what are called purely imaginary. Okay, so 3i and -3i, they have no real part. That's how you get this kind of stable elliptical trajectory orbits like this. So all that to say, the eigenvalue structure determines what kind of picture you're going to see. So the punchline of section 9.1 is this table, table 9.1.1, and it just walks through the cases of eigenvalues, tells you what kind of equilibrium you get and whether it's stable or not. So the first thing to point out is that we'll be hitting this table pretty hard throughout the rest of the chapter. Of course, you don't have to memorize this. Your exams are open notes and such from now on, right? Anyway, even if we were still meeting in class, you wouldn't have to memorize this. You just have to know this is what you want to grab. So the way you read it is as follows. This right here is saying I have two real eigenvalues that are distinct, both positive. Then you get a node and it's unstable. If they're both negative, real distinct, node, but now it's asymptotically stable, and so on. So anyway, here's just a table that's of use, right? And by the way, here, when it says the eigenvalues are complex, lambda plus or minus I mu, what if that lambda is 0? Lambda being 0 means purely imaginary eigenvalues. That's how I got that just raw stable thing, right? Not asymptotically stable, but elliptical orbit stable. If that real part is negative, that's how you get an asymptotically stable spiral. So things will spiral into the origin. On the other hand, if that real part is positive, you get an unstable spiral away from the origin. So things spiral, but away. So the way I want to conclude this video is by filling in some of the gaps from section 9.1. Section 9.1 in your text has two sort of curious gaps. The first gap is that they don't bother showing you all of these picture types. They only show you a few of them, which is odd. I guess they're saving paper space. The second oddity in the text is that this column here is supposed to march through all possible eigenvalue structures, but notice it does not. There's no entry here corresponding to the outcome where one of the eigenvalues is 0. Okay, so here everything is positive, here everything's negative, here one's positive, one's negative, so on, right? There's no entry for what happens when R1 equals 0. So I just want to show you that also. So to show you that, let's run over to Moodle. On Moodle, there's a section called Chapter 9 Images, and in here I have put pictures of everything that could possibly happen. They are labeled with their official name, and then in parentheses are how you get them. So an unstable node or unstable nodal source, whichever way you like to say it, comes from two distinct eigenvalues that are real, and they are both positive. If you click on that, you get this beautiful picture here. Notice it is a node. I've also in this picture included the two eigenvector lines. So we looked at this kind of thing in Chapter 7. You don't have to include these eigenvector lines, but I want you to see the node structure here. So notice one of these eigenvector lines is like drawing things to it. One of these eigenvector lines is acting like a sink itself. This other eigenvector line is repelling things, or it's throwing things off of it. So back in Chapter 7, we saw this came from, you have two eigenvectors, one dominant, one not, and the dominant one is associated with the bigger eigenvalue. So in this picture here, this line here must come from the bigger eigenvalue, and it's drawing trajectories to it. This guy here is less dominant, and it's throwing things away from it. So you can just sort of march through this. I mean, I don't want to show them all of you now, but like here's a stable spiral, complex eigenvalues with negative real part. Check that out, pretty nice. You get your spiral, right? So notice these trajectories are not ellipses. If you follow these arrows, you are forced to sort of spiral your way into the origin. So anyway, you can walk through all of these. The ones I want to point out, though, that the book does not have, when 0 is an eigenvalue, you can get a stable star point or unstable star point. Here's what they look like. This is stable, asymptotically stable, right? Being sucked in the origin just like straight. The trajectories are straight lines. There are no exponentials or triggy things to get you spiraling or curving at all. And then here's the corresponding unstable, like that. And as I'm making this, I realize I, of course, should have put asymptotically stable in all these spots, right? I have trouble updating my vocabulary from Chapter 2. So the only one of these that's actually literally stable is a stable center, right? Like this, these elliptical orbits. Everywhere else where you see the word stable, it should say asymptotically stable. Okay, so in the end here, after section 9.1, where are we going next? We have one last step to do before we can look at ecological models, and that step is as follows. This table and everything we talked about in this video still revolve around linear systems of DEs. I still have things that look like this, and I've surrounded these with language. The ecological models we'll study, like predator-prey models or competing species models, these are not linear systems. They cannot be written down this way. So the question is, what are these linear systems from Chapter 7 in this language? How do they help us study the ecological models we will build? Section 9.3 answers that question. It is a bridge from this table to predator-prey and competing species models.